Good day, everyone. It's my pleasure to host this webinar today, organized by Cell Press. As you may know, Cell Press is an all-science publisher of over 50 scientific journals across the life, physical, earth, and health sciences. We publish both independently and in partnership with scientific societies. Our forum today, Metaphotonics Revolution, Engineering Light for Tomorrow's Technology, will explore cutting-edge advancements in metaphotonics. We will focus on the remarkable capabilities of metasurfaces, discovering how engineered nanostructures can manipulate light to control polarization, enhance the chiral responses, and enable innovative optical functionalities. I am Dr. Kanuda Sharda, the scientific editor at iScience, an open access, broad scope interdisciplinary journal. Joining me are my colleagues, Dr. Yuan Yu from Device, a journal that publishes groundbreaking multidisciplinary research on applied technologies, and Dr. Chiming Ma from Cell Reports Physical Sciences, an open access journal dedicated to cutting edge research across the physical sciences and related interdisciplinary fields. We are excited to host this discussion today with our keynote speaker and panelists and address questions from the audience. Our panel will specifically focus on the theme of chiral and nonlinear metaphotonics of metasurfaces, two-dimensional layered materials, and ultra-compact lasers. I would like to highlight that many of the journals within the Cell Press portfolio, including Device, Matter, Newton, Cell Reports Physical Sciences, and iScience, regularly publish research related to the topics discussed today. Moreover, in addition to our premium journals, Joule, Chem, Matter, Newton, joining our new journals, Matter and Light and Cell Press Blue, that will have their first issues online in 2026 itself and are already open for submissions. As you see on this slide, Matter and Light will publish illuminating science and build community around materials and light interactions across scales, fundamentals to technologies in association with Matter Journal editors, with its first issue online in spring 2026. Cell Press Blue is another journal with publishing research with infinite potential and is a highly selected journal, open access, publishing cutting-edge research across all the topics mentioned and applied sciences, which is a platform carefully selected for curated articles with the potential of impact in academia, industry, and practice and beyond. Before we begin the talks, I would like to share a few practical points. Each speaker will present their latest research for approximately 15 to 20 minutes. Following the presentations, there will be a lively Q&A, providing an engaging platform for discussion. If you have a question for any of the speakers, please use the Q&A box on the right-hand side of your screen. You can submit questions at any time, and you can also upvote the questions you would like to see answered by clicking the thumbs up icon beneath each question. We will do our best to pass on as many questions as possible during the Q&A. It would be helpful if you include the name of the speaker to whom your question is directed. Also, this event is being recorded to watch later. Finally, at the top right of your screen, there is an option to turn on closed captioning. Click the CC button and select your preferred language. So, it is my great pleasure and honor to welcome our Professor Yuri Kivshar from the Australian National University as our plenary speaker. Joining him are panelists Professor Varun Raghunathan from IISc Bangalore, India, and Professor Hongyu Park from Seoul National University in South Korea. And kicking off with our first speaker, distinguished Professor Yuri Kivshar. Thank you for joining us today. Professor Kivshar received their PhD degree in 1984 in Kharkov, Ukraine. From 1989 to 1993, he worked at several research centers in the US and Europe. And in 1993, he moved to Australia, where he created the Nonlinear Physics Center at the Australian National University. His research interests include nonlinear physics, metamaterials, and nanophotonics. He is the fellow of the Australian Academy of Science, Optica, APS, SPIE, and IOP. He received many awards for his distinguished research, including Lyle Medal in Australia, Lebedev Medal in Russia, the State Prize of the Ukraine in Science and Technology, Harry Massey Medal in the UK, Humboldt Research Award in Germany, SPIE Mote Award in USA, Max Born Award Optica, and more recently, the 2025 Matthew Flinders Medal, a top award for the Australian Academy of Science. The title of Yuri's talk today is From Metamaterials to Metaphotonics. Yuri, the stage is all yours.
Thank you very much. I just tried to get connected. This is the wrong one. Sorry. Yes. Okay. I think cell editors for organizing this event and for attracting attention to many subjects in physics, in particular this fascinated new directions on metaphotonics. And my job today is to start from the very beginning, introducing the field, because it's definitely not subject which you can find in textbooks. And also give a platform for following talk by my young, enthusiastic, and outstanding colleagues on specific areas of this field. I'm trying to. Yeah. First, I start from the very, very beginning. So many of you know about light, and just easily switch on and switch off light in a room or anywhere else using torch. So light is something what everyone sees in their everyday's life. But light is actually, it's a physical object. It's a part of so-called electromagnetic waves family. So visible light, which all of you know and understand, is a very small or very restricted part of the so-called spectrum of electromagnetic waves, which cover a lot of different phenomena, started from radio waves up to gamma rays and X-rays, which you used for medical examinations. Electromagnetic waves appeared, concept of electromagnetic appeared long time ago, and from theoretical mathematical point of view, we may say that the origin of all these ideas was finalized, was specified by introduction of Maxwell equation. This is a simplified form of Maxwell equation on a Maxwell statue in the Edinburgh. Basically, this is one of the most important concepts in physics, with a multiple demonstration and application in everyday life. Some of the application of optics and photonics, particular light, which part of electromagnetic waves, it's already well known, and you definitely had the chance to meet with this application and enjoy this application through optical fiber network, communication with the photons, then data storage, this less common laser machinery, which used for different fabrication of different devices, and also for medical applications. There are many different manifestations of application of optical lasers and eye therapy in everyday's life. So it's very well established that optics is extremely important for our future life and future development of our technologies. And the question is how to implement that optical functionalities in the specific devices which you may actually use in everyday life. This is related to so-called photonic integration revolution, which is already ongoing for some years. And initially it was kind of relatively large, expensive devices based on electronics, and optics came into play, and optics on a chip, the silicon photonics type of devices were started to be important, introduced in ultra high bandwidth technologies and telecom application. And this is devices which can be integrated on a chip of order of centimeters. And the question is how to use these functionalities even in smaller devices with many more different type of applications. So our future actually suggests that we should reduce all these functionalities to the scales of order of micron, and then take photons to replace electrons for different type of application, and actually achieve some disruptive technologies for different areas of subject. And of course, the size becomes very important because you need to have smarter devices on much smaller scales. Question is how to get everything scaled to smaller sizes. And of course, this is a big question because we need to apply different knowledge and different approaches to make a next revolutionary step. And these approaches are associated with the so-called concept of metamaterials. So my job is to actually provide you background of what I will be presenting later today, and also my colleague will be presenting today. And this is not very common knowledge which you can't find in textbooks. So that's why I start to introduce a very, very first concept which actually started to be developed about 25 years ago. Of course, Meta, these days everybody knows Meta because it's associated with a media platform. But in our contents, Meta is somehow used to define something less usual. Meta actually the direct Greek word which means beyond. So in the concept of metamaterials, Meta was introduced about 25 years ago, and to basically define materials which can mimic what is actually nature does with normal materials. So basically all materials consist of atom molecules and with a particular packaging. So metamaterials operate with a bit larger object, a few hundred nanometers, so-called meta atoms, or even larger object if you're talking about microwave application. So these are artificial structures, usually artificial type of resonators, which are composed in different lattices, periodic or aperiodic. And basically this structure is controlled by properties of individual elements, which we call meta-atoms. So by changing meta-atoms, we may change properties of entire structure. And of course, size of that, several hundred nanometers, will not be visible. It's exactly what's happening in nature. You don't see atoms, you don't feel them. And the same with metamaterials. But in reality, just to give you impression what's happening there, these are structures which consist of these smaller elements. So basically, this structuring of materials is now a new type of trend to change properties, macroscopic properties of this object. This is basically the very general concept of different meta materials, meta surfaces, meta devices, and different type of things, because we are engineering elementary units. How it's happened? Actually, it's happened that people for electromagnetic application, they combine different type of resonances. First resonance is a so-called plasmonic resonance, which when excite strongly localized hybrid waves of combining electrons and electromagnetic waves on the interface of metal dielectric materials. So this is a kind of plasmonics associated resonance associated with so-called electric atoms. But what was a big discovery some years ago that we can actually control magnetic component of electromagnetic waves by introducing another type of element, so-called magnetic atoms. This is so-called magnetic resonances, which are in this simple geometry are excited by oscillating electrons, and combining magnetic and electric responses, we can actually engineer a response of both electric and magnetic properties of metamaterial. That was a concept which was created around 2000 years, and then 2025 was a special celebration of 20 years of discovery of metamaterials. A lot of interesting properties. This is one of the first structures. One of the properties was a so-called invisibility cloak, a possibility to engineer both electric and magnetic responsive to create a kind of shielding and hide an object. That was a lot of media attention. Invisibility cloaking is a very interesting concept, and people were very excited with many journal publications. That was basically one of the development of metamaterial, in addition to negative refraction, but everything was for much larger scale, and the question was how to bring all this development to optics and visible light. This came to the concept of so-called meta-optics. Idea was that currently using that time structures which were based on metallic component, we needed to actually move to platform of dielectric to actually have this magnetic properties of excited magnetic resonances. That took a bit of time to actually move from metallic structures with lossy elements to dielectric structures. An idea to actually replace resonances in metallic structures to resonances of dielectric structures was to use so-called me resonances. So basically the ideas which happens around 2010-11 was that for meta optics, for visible light realization of metamaterials, we need a new platform. So to create meta optics which will absorb different knowledge of metamaterials and will provide new elements and new functionalities which people discovered from metamaterials. This meta optics actually based on dielectrics was possible due to rediscovery of so-called me or functionalities of me resonances. Me theory is very well known and describe how a sphere made of any type of material actually react to external electromagnetic waves. So me solve Maxwell equation exactly and describe these modes which known like me resonances, and people did not realize for a long time that these me resonances may be associated with both electric and magnetic responses. And then if you excite individual elements based of high index resonances, you basically come to the simple technology platform which allows you, similar to metamaterials, combine electric and magnetic response of materials, and that somehow shapes the field which we now call me resonant photonics or metronics. Interesting story. The term was introduced around 2019 by editors of Photonics, Nature Photonics. was kind of sudden discussion and discoveries when we were interviewed with Mark Prosgesma from Stanford University by that time editor of Nature Photonics, Rachel Won, and that came to the idea that this field somehow relies on this elementary excitation produced by Mie resonances. It's a very interesting direction, which allows you to actually create structures with a very controlled responses to electric and magnetic field. And the most impressive manifestation of all the developments were, of course, not the individual particles, but the structures. If you now put this resonator on the surface, as you see, this is an artistic image of some structures we fabricate. We create so-called metasurfaces. Metasurfaces are usually flat structures composed of resonators. Metasurfaces actually led to another revolution, a revolution in optics. This is very fascinating development, which has many different manifestation, and basically idea is to actually replace all lenses which exist and produce through polishing of pieces of glass to something flat. This flat structure is composed of resonators, and this allows you to introduce the same functionalities for entirely flat surface. How it works? If you now look at the conventional lens, the concave and convex type of surfaces, which are usually polished, and metasurface, we have a very flat surface, which are composed of resonators, as you see shown here by these stripes. And this replaces lenses, which are with sizes several millimeters, to structures which are actually engineering along the surface. It's not very thin, but still it's of order of hundreds of nanometers or several hundred nanometers. Basically, you achieve similar functionalities like for normal lens, which are hard to fabricate and polish, by creating structures with a specifically designed surfaces composed of resonators. That's a revolution which is associated with the word of meta-optics and allow many applications of different types. And several years ago, with my colleagues from Singapore National University, we presented very recent in that time development of the concept of metasurfaces, showing that way it can be applied for biosensing, hybridization with two-dimensional materials, which will be mentioned today because where surfaces are both flat, and also with many other things like generation of photons from structures and quantum metasurfaces and computational and information metasurfaces for decode and uncode information. So it's a lot of things, and I just mention only these most recent developments, and even now we have already more different interesting things. The basic knowledge associated with metasurfaces is ways to control response, and that people in the last years we realized that you can control response of metasurfaces either engineering individual resonators, and then we call such metasurfaces local metasurfaces, or engineering longer structures, longer response of collective response, and then we call them non-local metasurfaces. This is a different type of strategies which allows you to achieve different functionalities. I will mention only about a few of them as examples. For example, for resonances, we actually explore so-called bound state in a continuum, interesting concept introduced for quantum mechanics a long time ago without understanding that how it may be affected, how it can be realized, and how it will affect optics application. This is a very interesting concept which allows you for quantum particles sitting in a potential actually introduce states which will be fully localized and will coexist, will exist in a continuum, but it would allow you to actually couple light with this localized states and decouple light, And that's what we use for resonances and metasurfaces. This example, so we engineer elements. These elements have some asymmetric profile, allows you to create a very sharp resonance. And these are examples of fabricated structures. You see that these are metasurfaces with specifically designed elements. And these elements have this asymmetry introduced, and this is also asymmetry. And the sharp resonance allows to do many different things with the structures and with their response to light. One of the examples I want to mention is so-called biosensing application. We create a metasurface consisting of smaller metasurfaces. Each of them has resonators, and each of them has a particular sharp resonance. This is scale, so we have 10 by 10, 100 pixelated metasurface. A metasurface is composed of smaller metasurfaces. We have a combo of resonances. And then if you use it for sensing, we just put the analyte and couple with mid-IR oscillations of particular substances. And what we can see without any spectrometer, we can record it and create so-called barcoding and associate the particular substances with barcoding library. And this is one of the original ideas how to use these sharp resonances for biosensing. There are many other ideas and ideas how to expand it to hyperspectral biosensing, and now there are many applications, interrogates and demonstration of the similar ideas with multi-resonant type of metasurfaces. Very recent developments is based on efforts to actually combine local response from particular meta-atoms and non-local response to create very sharp and high Q collective resonances and create a so-called meta lasers, which will allows you in a flat surface covered by gain material to produce any laser beam of any type of shape. That was demonstrated and recently published in Nature, and probably still will take a moment to realize particular different application. Finally, I'd like to mention that this ability to engineer meta-atoms allows you to control chiral responses of metasurfaces and metaphotonics. This is a very hot topic, and the idea associated with the possibility to achieve a very sensitive chiral sensing, separating of molecules by their chiral characteristics. And this basically comes to the very old days of pioneers in chiral properties and knowledge was associated with introduction of circular dichroism, a response of materials and substances to light of different circular polarization. And people initially tried to enhance circular the chiral response because chirality in natural materials are very weak, through introducing this, plasmonic structures you see with spirals. So spirals pitch of order of wavelength of light and actually make different response to right and left polarization. But of course, these plasmonic structures are very lossy, and it was not clear how to actually make a lossless and highly sensitive structures which will react to different types of circular polarization of light. That became possible. This is chiral plasmonic, this is even seven years ago. It became possible through introduction of this bound state in a continuum, sharp resonances. This is a very first theoretical paper which predicted that type of response which will be highly sensitive to type of circular polarization of light, right and left. You see that transmission depends very much of type of circular polarization. And one of the application was demonstration of a chiral laser, which will emit light of particular polarization. And that is achieved through interesting engineering of metasurfaces that give you example how we can actually operate and engineer with these elementary units. Initially, we start from symmetric metasurface composed of symmetric resonators, and then basically we change profile and incline them, making slantic resonators. And this control of vertical dimension allows you to actually achieve preferential interaction with particular circular polarization. And then what we can do, we can basically achieve lasers which will be with relatively low threshold, but will separate right and left circular polarization. Metasurfaces based on lasing based on metasurfaces will be presented by Professor Park later on, but I just wanted to show you that there are different approaches, but all these approaches actually based on the simple idea that we can manipulate with these individual units achieving particular functionalities. This is a slide which gives you idea, which may give you idea of scope of different application. I pick up directions which are associated with my former students and my former postdocs and the current directions. So just to show you variety of possibilities. So we can, with metamaterials, we can control invisible solar panel contacts. This is important for industry of solar energy harvesting, because contacts produce several percentage of losses, and this is very important. Metamaterials can be used for security screening. This is prototype for security screening, which will completely replace the currently arranged huge delay and bottlenecks in airports. And this is stealth technology, apparently based on the metamaterial concept. It's a race of antennas which make aircraft invisible. Of course, you can't read about that in normal journals. MRI can be enhanced signal quality and reducing time, may be enhanced with this particular metamaterial pads. And there's already companies which produce that. And the more recent developments in the holograms created in your iPhone, and of course, sensors created, installed in your iPhone. That's all this technology is coming, and it will be based, and it's heavily based on this concept of metamaterial. Coming to the end, I just wanted to make a very few general statements. So metamaterials is a new exciting field of research. And basically, the concept is that we create artificial structures based on some units, engineer units, that change properties of entire structures. That's a very, very basic concept of everything. And of course, when we managed to move from microwaves, we managed to move to optics. This reshape or rebranded that field. Now we are talking about meta-optics, beyond optics, and metaphotonics, beyond photonics. We are dealing with quantum light, and that's majority of all this effect are based on resonances, because resonances are important to specifically control particular responses. And of course, metasurfaces is implementation of metamaterials for so-called flat optics, and that will help to replace bulky optical elements, particularly in conventional lasers. There are 22 companies right now which actively research all this application. Of course, the most important, as always, in any scientific discovery is to get it relatively cheap. So as soon as we create something cheaper, you can apparently expect that it will be going to market, and people will enjoy all these technologies which already developing in the scientific labs. Thank you very much for your attention, and thanks Cell people who actually arranged that webinar to make these activities more available for public. Thank you very much.
Thank you. Thank you so much for the insightful talk, Yuri. I'm sure you have formed a solid understanding to follow up fundamentals, but also updated every one of us to follow on the research applied and to the latest technology and the following talks. So moving on, let me introduce speaker number two, Professor Varun Raghunathan. Varun is currently an associate professor at the Department of Electrical Communication Engineering at the Indian Institute of Science in Bangalore in India. His research group works in the areas of nonlinear optics, integrated photonics, resonant metasurfaces, optical communication, and quantum communications. He received his PhD degree in electrical engineering from the University of California in Los Angeles in 2008, working in the areas of silicon photonics. From 2009 to 2012, he was a postdoctorate fellow at the Department of Chemistry in University of California, Irvine, working in nonlinear optical microscopy. From 2012 to 2016, he was a research scientist at Agilent Research Laboratories in Santa Clara, working in the areas of infrared microspectroscopy and applications of optical techniques to tissue imaging. The title of Warren's talk today is Nonlinear Metaphotonics with Two-Dimensional Lead Materials. Warren, please take it away. Thank you.
Okay. Thank you very much, Kanuda. So thanks for this opportunity to present some of our work. So I'll be talking about a specific application of metaphotonics in the area of nonlinear optics, and also choose a specific material system, two-dimensional layered materials, and also may try to make a convincing case why this is an interesting material to study. Um, so this is the outline of what I have planned. Just to make sure everybody is in the same page, I'll talk about some basics of nonlinear optics, and then why study nonlinear optics in nanoscale or sub-wavelength scale platforms, and then move on to a specific work we have done recently in the enhancement of nonlinear processes, specifically second harmonic generation in isolated molybdenum disulfide disks. So I'll take you through some of the design, fabrication, and also the experimental work to understand some of these structures as well. The work I'm going to talk about is something we published in 2025 in the journal Advanced Materials. Basics of nonlinear optics. So what are we talking about here? We are talking about light interaction with matter at high optical intensities. So what happens is that when I shine light of high optical intensity on a material, I can understand the individual atoms kind of responding to that high intensity. So in essence, it's the electric field which drives the oscillators. The atom and the electrons, the valence electrons, respond like a harmonic oscillator for a linear optical process. And if I drive it hard enough, then it becomes anharmonic. The consequence of that in electromagnetic theory, I would be able to write it down as a polarization field, which is made up of not just a linear term, which is directly proportional to the electric field, but now I have interesting wave mixing terms because of the quadratic dependence, cubic dependence, and so on. Right? So that creates a lot of interesting optical processes. I can look at wave mixing, frequency conversion, intensity dependent changes to refractive index, and a lot of other interesting properties can be studied. Where is nonlinear optics used? There are a lot of practical applications for nonlinear optics. For example, if you at all use a green laser pointer, invariably it is a harmonic, like a doubling crystal, which is used inside it to generate green wavelength. There are also a lot of interest in photon pair generation for quantum applications as well. The heart of it is a nonlinear crystal, right? And two important considerations when we talk about nonlinear optics is energy conservation, which directs the direction or the energy of the photon which is being generated, and momentum conservation, which decides the direction of photons or its dispersion properties of the structure in which it propagates, and so on. So what are the nonlinear processes we study? Just again, very high level overview. We study different processes like harmonic generation with two photons combining to give rise to a second harmonic, or three photons combining to give rise to third harmonic. There are also wave mixing processes where I have two different energy photons. We give rise to a third photon at a higher or a lower energy. And all these three processes are parametric in the sense nothing is lost to the medium, but there are processes where energy is also taken up by the medium. For example, multiphoton fluorescence is a very important process there. And also there are Raman optical nonlinearities. You can drive phonon modes or vibrational modes in materials as well, and study their nonlinear optical response as well. Right? So all these processes find useful applications. For example, Raman nonlinearities are used to build Raman amplifiers. Multiphoton fluorescence is used as an imaging technique to look at tissue samples and so on. So there are a whole array of applications which have emerged over the years in studying or leveraging these nonlinear processes for something useful, basically. Right? So then moving on to what are the kind of material platforms in which nonlinear processes are studied. If you look at some of the popular work, you find long interaction materials like optical fibers, where people use kilometer long nonlinear media to study optical nonlinearity. And that has been something which has been popular since, I would say, the 80s, where people have studied a whole range of nonlinear processes. Then if you look at an even smaller scale like bulk crystals, then we find that the length scale gets reduced to maybe few centimeters, maybe tens of centimeters. So there's a huge hit in length, right? The interaction length. And the way that is often compensated is by going for materials with strong optical nonlinearity, going for crystals, going for non-centrosymmetric materials like lithium niobate, KTP, BBO, and a lot of other bulk crystals have been used to build useful devices. And then if you look at maybe around 90s and early 2000s, there was interest in shrinking the optical mode to a much smaller spatial scale, and then still guide it in guided wave structures. For example, silicon photonics, and more recently thin film lithium niobate photonics has also come up, where the lengths of interaction are even going down to maybe centimeters or millimeter, and you compensate for it by an increase in the optical intensity due to tight optical confinement. So if you follow the same trend, what do we expect to come up? Then I can expect devices which are going down to maybe micron scale in length. And then there's a huge hit in terms of interaction length. And the way we try to compensate for it is by going for materials with even higher optical nonlinearities, or probe materials at wavelengths where it will respond resonantly. Or the other approach to take would be to enhance the electric field, right? It's the electric field and its quadratic and the cubic terms which drive the nonlinearity. So if I can enhance the electric field by a factor of maybe 10 power 2 or 10 power 3, then that can have a huge impact in enhancing the optical nonlinearities, basically. And then if you see what has been happening in this field over the last decade or so, people are exploring material platforms, especially metasurfaces, like what Yuri was talking about, leveraging the field enhancement, right? What you get in resonant metasurfaces to enhance optical nonlinearities as a direction of interest. And in terms of exploring novel materials, there's been interest in exploring 2D layered materials and then studying their nonlinear optical properties. And hopefully these will also find device applications in the future. So what are the work that has happened in studying nonlinear optics in metaphotonic structures? So one of the earlier work, I think Professor Yuri was also part of this. They were looking at isolated silicon disk structures, and then relying on the intrinsic me scattering modes, for example, magnetic dipole type resonant modes from these structures, and then using this to resonantly enhance third harmonic generation processes in these kind of structures. In fact, the third harmonic is so bright that you can even see the blue color in a camera image which was taken from this sample. Subsequently, people have started looking at arrays, coming up with interesting resonance mechanisms. I think quasi-BICs is one popular resonance mechanism to achieve high quality resonances. So even that has been used to enhance optical nonlinearities. So this is a silicon metasurface with an intentional asymmetry which has been introduced, and that creates very sharp, high quality resonances. So this has been used to study both third harmonic and also second harmonic from centrosymmetric silicon structures. And then there's also work on studying higher harmonic generation from interesting platforms. For example, these are like holes instead of disks which have been patterned. This is a membrane of silicon where you see arrays of holes. Again, it supports interesting scattering modes, and then one looks at collective effect between arrays of these scatterers. And then you can make use of the strong field enhancement in the silicon material, and then look at lots of odd harmonics which are being generated all the way to ninth harmonic and so on. And then there's also interest in applications, right? How to use this for useful frequency conversion. So one area of interest which has taken off is this kind of projecting images onto this metasurface, and then wide field, like the large area, whatever is being projected, trying to upconvert it to other frequencies. A driver here is like if you have infrared images which are difficult to detect with an infrared sensor, then one could potentially convert it to a wavelength where I can use a standard silicon sensor to do imaging and all that, right? So all these are areas which have come out of this metasurface and understanding the metastructure physics and then applying it to nonlinear frequency conversion type applications. So if you look at all these structures, a general trend which you see is that some of the scattering modes which are supported in these structures are strongly influenced by the refractive index of the medium, right? So what I show here are two different prominent scattering modes. The one on the right side is because of the magnetic dipole type resonance, and one on the left is because of the electric dipole type resonance. And as you can see, as I increase the refractive index, this is just a standard disk, an isolated disk. As I increase the refractive index of the disk, these resonances get sharper and sharper. The reason being that light wants to confine itself into a high refractive index medium, strongly interact, and correspondingly scatter more efficiently through that. And as light strongly interacts with high refractive index medium, there's going to be a higher electric field which is going to be set up in this material, right? So that is something which I would like to leverage if I'm studying the nonlinear properties coming out of these kind of isolated meta atoms. So if you study nonlinear optics in any material, right, it's the material, it's the interplay between the material and the electromagnetic field which is of interest. So if I want to select materials, I want to go for materials with high refractive index, right? But nature is generally not so kind, that we find that when I go to high refractive index material, the band gap of the material starts reducing, right? So that could be a problem, because when I generate my harmonics, it could be at a wavelength where the material will start absorbing, and then now I cannot efficiently collect that light coming out of my metasurface, right? So then there is interest in exploring materials or new materials which kind of beat this rule, that what is shown here is essentially the refractive index versus band gap. So as I go higher in refractive index, the band gap of the material reduces. Then I want to look at outliers which do not follow this trend, right? So people are looking at materials. So this trend, whatever is shown here, is what is known as Moss law, and which has been published in the past. And then people are looking at materials which violate this rule, which are called as super Moschian materials. Two of the popular materials which were identified are shown here. One is iron pyrite, FeS2. The other are this whole class of transition metal dichalcogenides like MOS2 and so on, right? So there's a lot of interest in studying or building metasurfaces out of this, and then studying the light interaction. And for our interest, we are trying to explore the kind of nonlinear photonic properties which these kind of material platforms will offer. So moving on, why do we study nonlinear optics in these kind of layered materials? One motivation is to violate this Moss rule, and then go beyond that to achieve wide bandgap materials with high refractive index. But then if you look inherently at these kind of layered materials, especially I'm focusing here more on the transition metal dichalcogenides, monochalcogenide like platforms. The transition metal atom is essentially made up of these d shells of electrons, and then they essentially screen the valence electrons quite a bit, right? So when you drive these oscillators nonlinearly, there you can create strong polarizations at these which respond nonlinearly, and then you generate enhanced nonlinear response from these kind of materials. So inherently, these transition metal dichalcogenate systems, especially in its crystalline form, exhibit strong optical nonlinearity just because of the way these electron shells are arranged in these atoms, basically, right? So I would like to leverage that property, the combined properties of having very good linear optical properties, and the way that I can drive these nonlinear oscillators with quite a bit of strength, that I want to combine these two effects and try to make use of this for useful device applications, right? On top of that, there's also this whole field of using these 2D layered materials, both in monolayer and also multi-layer form, for electronics applications as probably potential replacement or maybe an addition to a standard silicon transistor. So that's also an emerging area which is coming up. So as more and more investment goes into this in fabrication and all that, we can leverage that when we study these the photonic properties of these materials as well. So our group has been focused on studying nonlinear properties of layered materials for almost last 6 to 7 years. So I broadly categorized some of our research efforts into these 4 categories. We have been studying layered materials, just trying to understand the nonlinear properties, right? No patterning or nothing, but just study. Like if there is a new material which comes up, then is this good for nonlinear optics or not? Is an area is something we work on. So trying to characterize like how strong is the optical susceptibility is something of interest. For this, we collaborate with a lot of groups around the world who send us samples. We study their properties and so on. And then now a basic level of integration would be to build multi-layer stacks. So you can think of it like a DBR reflector or a Fabry-Perot kind of very simple stack, which can be used to enhance light interaction with these kind of structures. So I can design this stack carefully so that there will be a strong electric field which is set up within the layered material. So that is a promising direction we have explored. And then one more area of interest are these hybrid integration or hybrid metasurfaces, where there could be an underlying silicon metasurface platform on top of which I can transfer layered material. So a lot of groups around the world are also exploring these kind of ideas, where I leave the high quality resonance to the underlying silicon metasurface while I leverage the nonlinearity offered by the layered material and then build these kind of composite platforms for nonlinear applications. And then one more area which has come up over the last 2-3 years, I would say, is to have the ability to pattern these layered materials and build resonance structures out of these, right? So this is an example. This is just a cartoon schematic of a disc, molybdenum disulfide disc, which we have been also working on. A lot of groups around the world are also addressing this, where one can leverage the high refractive index to enhance the scattering properties and then use this for nonlinear photonic applications. Right. So what is the workhorse? Like, how do we do experiments in the lab? The workhorse, what we have is this nonlinear microscopy system, whatever is shown here. We use pulse laser systems to kind of excite these samples. It's like a microscope, fairly generic system. So all the 4 samples I showed you can be put on the sample plane of a microscope, excite with different colors, and then try to look at their nonlinear response. So it's a fairly robust system. So these are a couple of examples of how nonlinear microscopy is very useful if you want to study layered materials. So this is an example where we have looked at twisted bilayers. These are essentially MOS2 and WS2, which are intentionally twisted a little bit to create these Moire hotspots or Moire potentials. And a golden standard to measure the twist angle is to make use of second harmonic generation. So we look at the polarization response in the second harmonic, and the slight twist, whatever is shown here in the polar plot, gives me an accurate estimate of how much is the twist angle between the 2 layers. And similarly, we have also looked at different polytypes of materials you can grow. So this is an example of a 3R polytype of MOS2, which is supposed to show layer independent nonlinearity, which is also something we have characterized. And this is a collaboration with a group here in India. So moving on, so in terms of metaphotonics, we have been looking at these kind of MOS2 disk structures. I've already motivated why we study this. It offers very good optical properties like broad optical transparency, high refractive index. Some of the refractive index numbers which have been reported in the visible are like a refractive index in the range of 5 to 6, while in the near IR wavelengths, people have reported refractive index of about 4, 4.5 type numbers. So they are fairly high, while the band gap wavelength is about 750 to 800 nanometer. So it's a fairly good material if you want to use this for frequency conversion, harmonic generation type applications. The kind of structures we have been looking at are very simple disk resonator structures. If I look at an isolated disk resonator, we design the dimensions of these disks to support scattering modes, which are called as anapole resonances in literature. So what these resonances are essentially the kind of scattering modes which are supported in an individual disk, but now it's made up of an electric dipole mode and a toroidal mode, which essentially interacts with each other. And at a particular dimension or a particular wavelength for a fixed dimension, you get kind of a destructive interference between the two in the far field, that you essentially get like a dark state that you wouldn't see any scattering coming out of it, but locally there is a strong field enhancement because of the interaction between the two, the electric dipole and the toroidal mode. So these are typical field profiles which we obtain when we look at these kind of resonances, and then we design these structures by choosing an appropriate diameter where you can park one of these dark modes which is shown by these bands at a particular wavelength of interest, basically. right? So then what we do is we introduce the underlying layers, right? I cannot study a disk hanging in air, so I have to support it by a silicon dioxide layer and a silicon substrate. So when we build these stacks, we find that there's some interesting effects which occur. The silicon dioxide layer is a low index medium sandwiched between the MOS2 disk, which is of a high index, and a silicon substrate at the bottom. Then there are going to be interesting Fabry-Pérot modes which are going to be set up in the silicon dioxide layer. And what we find is that these bands, whatever I showed in the previous slide, they become a lot more pronounced in the sense that there are specific diameters where there is a strong enhancement in the energy which is stored within the disk. The reason why this occurs is that there's an interaction between the Fabry-Pérot mode and the anapole scattering mode supported in the disk, and that's what enhances the overall energy much further than what you would see for an essentially an isolated disk. So this is something we would like to leverage in whatever we are doing subsequently for studying the nonlinear properties. So we went ahead and fabricated some of these structures in the Indian Institute of Science clean rooms. So what you see here is an exfoliated MOS2 flake, and then we do electron beam lithography to define disks of different diameters, and then study initially their linear properties. So this is just looking at the reflectance, which is an equivalent measure of looking at the scattering, though we don't collect all the angles, but still we can get a good spectral feature which resembles the dark state. And then the other sign what we are looking for is that as I increase the diameter of these disks, there's a clear shift in these resonances, right, which is also seen. And then the other feature is that the contrast in these resonances tend to go up as well for an optimum disk diameter, which is also of interest to us because we have intentionally designed for a specific disk diameter where I get this constructive interference between the Fabry-Pérot and the anapole scattering mode, basically. Right? So then we went ahead, put these samples in our microscope system and started looking at the second harmonic response. And what we found was that corresponding to the dips, what we saw in the reflectance spectra, you can see peaks in the SHG spectra because those are the wavelengths where the second harmonic response is going to get enhanced. And then when we quantitatively compared this with an unpatterned layer, right? I can go outside these disks and then measure the SHG. We do obtain significant enhancements in SHG. For one of these diameters, we obtain like nearly 160 times enhancement. And the other interesting thing also we observed is that we can also compare this with a monolayer, right? A monolayer is like just a single layer of MOS2. There again, we obtain a significant increase, like nearly 100 times increase in the response. I'll explain why this is interesting in the two slides I have subsequently. So these are not done only across few disks. We have tried it across like nearly 40 to 50 disks. And then we observe a clear trend in the sense that the diameter of these scatter plot shows the strength of the SHG signal that is being enhanced for a optimum value of the disk dimension. And then we also see clear trends for different diameters and so on. Right? So the reason why I was comparing with monolayer is that if you look at the particular polytype or the way these layers are stacked, the dipoles, the nonlinear dipoles tend to cancel each other out. So it's the monolayer which gives the highest second harmonic, and anything even, you get a cancellation in the dipoles. And then as I stack them bigger, like thicker and thicker, there's going to be a reduction in the SHG signal. Right? But then we were in fact able to observe an increase in the SHG signal with stacking and fabricating the disk. The reason for this is very interesting, that you not only create a strong field enhancement within the structure, but you also create a strong field gradient, right? The consequence of the field gradient, right, because there's a rate of change of field with respect to the height of the structure, I find that those dipoles, right, no longer cancel each other out. So that makes it even more interesting because that lack of cancellation enhances the overall second harmonic significantly when compared to if I were to choose only a monolayer of these materials. So the disk structure not only helps in increasing the field strength, which is used to study optical enhancement, nonlinear optical enhancement, but it is also very useful in creating field gradients, which are used to essentially break the asymmetry in the way these dipoles are oriented. So that makes it even more interesting. Right? So then we went ahead, did some modeling with COMSOL, and then tried to compare it and all that. We were able to get very good agreement with this as well. Right? So I think my time is running out, so I'll stop here. I hope I have convinced you that 2D layered materials is an interesting platform to study nonlinear optics, and particularly patterning them is a promising approach to leverage some of the advancements in metaphotonics, the individual scattering modes, and also if you were able to realize arrays, that also makes it that much more interesting. I discussed one particular application of second harmonic enhancement in these MOS2 disks, but then this field is just starting up. A lot of interesting things are coming up around the world as well. Right? Okay. Thank you. I'll stop here. Yeah.
Thank you. Thank you very much. Thank you, Arun, for the insightful talk and your latest research. Our best wishes with you. So moving in the interest of time, it's my pleasure to introduce our third and the final speaker. And it's my privilege to introduce Professor Hongyu Park from Seoul National University from South Korea. Professor Park received their PhD in physics from KAIST in 2004 and completed their postdoctoral training at Harvard University. He's currently a full professor in the Department of Physics and Astronomy at Seoul National University. He's a fellow of the Korean Academy of Science and Technology and an Optica fellow. His research focuses on topological nanolasers and nanoscale photonic and plasmonic devices, as well as optical applications in low-dimensional materials. The title of Professor Park's talk is Strong Nanophotonic Interaction for Lasing and Single-Photon Emission. Please.
Thank you very much for your nice introduction. And just my name is Hongyu Park. I'm from Seoul National University. And first of all, I'm very happy to give a talk in such a great webinar series. And thank you very much. And thank you, Dr. Sharda, for your thoughtful invitation. And today, the title of my talk is Strong Nanophotonic Interaction for Lasing and Single-Photon Emission. So my talk will consist of two parts. And first one is nanolaser, and the other is single-photon emitters. And first part is a nanolaser, and this part will be presented based on this paper published in 2024. And the Yuri is corresponding author of the paper. And I want to briefly introduce nanolaser timeline, first of all. And around 2000, photonic crystal, as you know very well, consists of a periodic array of two dielectric materials. And photonic crystal laser can exhibit high quality factor and small mode volume. And around 2010, plasmonic cavity or metallic cavity can support very strong light confinement within a diffraction limit. Since then, since 2010, more fundamental physics mechanism have been included to demonstrate nanophotonic cavities. For example, parity time symmetry breaking, bound state in the continuum, and photonic topological insulate mechanism have been included to demonstrate photonic cavities. More recently, Moira-inspired nanolaser and disclination nanolaser have been successfully demonstrated. So today, I'm going to focus on disclination nanolaser. First, I want to explain just orbital angular momentum of light. Simply, OAM is very good quantum number and particularly useful for generating different degrees of freedom for specially distinguishable channels in data transmission. So, coherent OAM light sources have been demonstrated successfully using micro-ring resonators, photonic crystals, and pillar chains. But these are all some bulky size and micron size, so substantial scattering loss and high lasing threshold cannot be avoided. In addition, there is no report about intrinsic vortex mode generating OAM characteristics. So to address this issue, just my group is focused on the topological features, especially topological disclination state. So this is very interesting feature. First starting point is C4 lattice, four-fold rotational symmetry, and cut into four sectors like that, and add one sector or remove one sector. So we can generate C3, three-fold rotational symmetry, or five-fold rotational symmetry structures. More interesting thing is, four corner charges originally in the C4 lattice can be confined in the bound state in the core as a result of a disclination procedure. So also that corner charge called topological bound state can have angular momentum. So we want to mimic this feature to generate disclination nanocavity. So we design photonics version of disclination cavity generating vector vortex states such as optical vortex and optical anti-vortex. In addition, we use similarities between tight binding simulation and optical simulation. In tight binding simulation, charge density is confined in the atomic site shown like black dots. And also periodicity of this atomic site, energy band gap can be generated. Similarly, in optical simulation, the black dots correspond to air holes, and magnetic field can be confined in the air hole region if we consider transverse electric case. And also photonic band gap can be generated due to the periodicity of air holes. So using that similarity, we design the photonics version of a disclination cavity. So our design strategy is very simple. So starting point is again C4 lattice, and using voltage process or disclination procedure, we can make C3, C5, and C6 disclination structures. And then these black dots can be replaced into air holes to make photonics version of disclination cavity. And then just like a fractional charge, photons can be confined in the core region, and fractional charge can have angular momentum. So also photons can have angular momentum. So we can check this feature by comparing tight binding simulation and optical simulation in two-dimensional case. So there is one-to-one correspondence between tight binding simulation and optical simulation in C5 disclination cavity. You can see L0, L plus minus 1, and N plus minus 2, 5 in-gap state in tight binding simulation. And similarly, in optical simulation, there are 5 resonant modes, L0, L plus minus 1, and L plus minus 2. This one-to-one correspondence between geometric and photonic in-gap state with the same angular momentum is originate from the similarities between tight binding simulation and optical simulation. In C3 and C6, there is strong one-to-one correspondence. There are 3 in-gap states in C3, and there are 6 in-gap states in C6 disclination structures. So we further interested in these two modes, L0 and L plus minus 2 in C5 disclination cavity because they have central singularities in the electric field. So we can derive exact form of electric fields just like that, L0 and L plus minus 2. There are 2 degenerate modes in L plus minus 2 electric field. In addition, we calculate topological charges using this equation, and then L0 mode has topological charge of +1, and L plus minus 2 have topological charge of -1. So L0 mode is vortex mode, or in conventional optics, it is called azimuthal polarization state. And L plus minus 2 mode, anti-vortex mode, this is called even and hybrid polarization state. So we extend our simulation to real 3-dimensional case. So we employ the photonic crystal slab structure and repeat the same simulation. The results are exactly the same. So electric field intensity and vector distribution indicate azimuthal polarization state with a singularity at the center. And phase distribution indicate counterclockwise closure loop, which indicate topological charge +1. More important thing is high quality factor and wavelength scale mode volume. And also that core region is the singular point. So we can modify freely to excite another resonant mode. So we shrink the core so we can excite degenerate anti-vortex mode like that. In this case, topological charge is -1, while the mode volume is very small. So based on these well-designed optical cavities, we actually fabricate the samples using 280 nanometer thick indium gallium arsenide slab with 3 quantum wells. So the cavities are optically pumped at room temperature, and each cavity exhibits clear lasing features, including sharp single-mode peak and superlinear increase above the threshold. So this vortex mode has just a single peak, and this anti-vortex cavity support 2 doubly degenerate lasing mode. To identify this lasing mode, we measured polarization result mode images without the polarizer first case, and all 3 modes exhibit donut-shaped intense profile, which is a unique feature of vector vortex mode. But with polarizer, the images are very, very different, very distinguishable. The vortex mode exhibit the azimuthal polarization state, and these 2 doubly degenerate anti-vortex mode exhibit the odd and even hybrid polarization state. And those measurement results shows excellent agreement with the simulation result. To identify the lasing mode in more detail, we also performed specially resolved Stokes parameter experiment. To do that, we need complete set of polarization resolved mode images, including horizontal, vertical, diagonal, anti-diagonal, right circular, and left circular polarization images. And these are raw data, and using the equation, we obtain Stokes parameter images, and S0, 1, 2, and S3. And these Stokes parameter conform the lasing mode with topological charge +1 and 2 doubly degenerate -1 values. And I want to highlight this table because we want to compare our disclination laser with other vortex, nano, and micro lasers. I want to highlight the very low threshold value, just 100 times smaller than the previous cases, because the cavity size is 1,000 times smaller than the previous nano lasers. More recently, we successfully demonstrate C6, 6-fold rotational symmetry photonic disclination nanolaser, and we added 2 more sectors in this C4 lattice cavities, and we fabricate a sample, and we successfully observe single-mode lasing peak. More important thing is polarization resolved mode profile. So with rotating the polarizer, interesting thing is laser mode complete just half rotation. That is unique feature of rotation order of 2 or topological charge of 2. So we successfully demonstrate C5 and C6 disclination nanolasers. So I want to make a transition to the second topic, single-photon emitters, based on this paper published in 2024 also. So you know very well quantum communication, and that quantum communication is typically based on Bennett and Brassard protocol, simply BB84. And BB84 consists of 3 parts. First one is sending polarized single photon through quantum channel. Second is conformation through public channel. And last one is sharing the specific key chains. But most important and difficult part is generation of polarized single photons. In addition, the quantum emitter should be strongly integrated with high-quality optical cavities for practical single-photon emitters. And then this, as shown in this equation, radiative rate of quantum emitter can be controlled. So to enhance pulsar factor, the emitter should be controlled in their position, spectrum, and polarization. But these are always very difficult. So people try to use 2D materials because 2D materials with inherent mechanical flexibility and strength can provide an ideal and robust platform for practical single-photon emitters via strain engineering. So my group successfully demonstrate the single-photon array using monolayer tungsten diselenide. First, nanogap should be fabricated underneath the monolayer tungsten diselenide, and this nanogap induced tensile strain and localized exciton rise from a confined potential caused by a local strain gradient, which leads to quantum funneling and single photon emission. And also 2-dimensional, in this case, 1-dimensional photonic crystal cavity is placed onto the monolayer tungsten diselenide single photon emitter, and then Purcell factor can be increased. But still, manipulation of polarization properties, especially circular polarization properties of single photon emitters, remain challenging. So we want to combine the monolayer tungsten diselenide with chiral gold nanoparticle. And strained tungsten diselenide monolayer coupled with chiral plasma gold nanoparticle can emit right circular polarization or left circular polarization depending on the coupling orientation. So fabrication is very simple. Just disperse chiral gold nanoparticle onto the silicon dioxide substrate and measure the second order correlation function, simply G2 factor, G2 value using HBT measurement setup. And then we successfully demonstrate single photon features, very narrow emission peak and G2 value below 0.5, especially in our experiment, G2 value range from 0.1 to 0.3, which shows high single photon purity. And then more important thing is, interesting thing is polarization resolved spectra. So in this sample, so we observed dominant left circular polarization spectrum while single photon emission feature is still observed. So G2 value is below 0.5, but only red curve, left circular polarization is dominantly observed. And black curve, right circular polarization spectrum is strongly prohibited. To analyze more quantitatively that feature we measured Stokes parameters. And in this case, S3 value is more important because S3 is intensity of right circular polarization minus intensity of left circular polarization. So we measured S3 value of minus 0.8, and that means left circular polarization is dominant. And the other sample indicate just right circular polarization dominant single photon emission. So in this case, S3 value or degree of circular polarization DOCP value is 0.5, which indicate right circular polarization is dominant. But interestingly, just if we use gold nanocube without chiral nanoparticle, just there's no difference between right circular polarization and left circular polarization. So chiral nanoparticle is real origin to generate right circular polarization or left circular polarization. So to understand that issue, so we performed optical simulation. So key origin is dipole moment generated by tensile strain on the corner of the chiral nanoparticle. So if this dipole moment is oriented along the horizontal direction, left circular polarization is dominantly radiated. But dipole moment is aligned along the vertical direction, right circular polarization is dominant. That dipole moment is aligned along the 45 degrees angle and linear polarization is dominant. But in the nanocube case, only linear polarization is dominant regardless of the orientation of dipole moment. So we also demonstrate the particle array and also single photon array was successfully demonstrated. The generation yield is very high, 75%. So I want to conclude my talk. So I talked about two topics, vortex and laser based on a photonic discrimination cavity, and second topic is manipulation of polarization properties of single photon emitters. And so I want to thank my whole team and current members, and especially thank Professor Yuri Kivshar, his strong support and collaboration. And thank you very much.
Thank you very much for your insightful talk. I'm really happy to that we all named this webinar as Metaphotonics Revolution, because indeed, as our all speakers described, we are in the revolution phase, and it's so exciting to see everything happening. Once again, I would like to thank all the speakers for their valuable contributions, and I would like to hand over the floor for Q&A and discussion with the audience. So please keep your questions coming in. And invite all the speakers back on stage with their cameras on.
Hello. Yes, so if there's no additional questions from the audience, I guess we'll just ask general questions for Professor Kivshar. So we can see in the Q&A session here. So the question is, what are the strategies that can be used to improve the conversion efficiency of nonlinear optical processes in the metasurfaces? Do you have any thoughts?
Okay, I can take a shot at that. So
sure.
Often, yeah, to improve conversion efficiency, it's good to use lower optical nonlinear orders of optical nonlinearity. So in general, second order nonlinear processes tend to have higher conversion efficiency than third order and fourth order. And as you go up the order, the efficiencies can go down. So often the second order processes seem to work well if you were pushing the efficiencies. Then choosing materials with strong optical susceptibilities is good to have. And that's where a lot of the 3-5 semiconductors, lithium niobate, all that is becoming popular these days. And then from a meta structure perspective, it's also good to design resonances with high quality so that there is going to be huge field enhancements within the structure. And that's what we want to make use of. Okay. I hope I have answered your question.
Anything to add, Professor Park and Professor Kivshar? Oh, if there's nothing, then let's move on to the next question. So is it preferred to have resonance at the excitation frequency or the emission frequency for this?
I think Professor Kivshar can take this, if it's okay.
Yes. Anybody want to take a shot at
it? You're muted, Professor Kivshar.
Oh, sorry. The reception is not very good. Can you please repeat the question?
Yes. So the question is it preferred for these devices to have the resonances at the excitation frequency or the emission frequency? I will pin also the question at the top of the Q&A as well.
Oh, wow. Yeah, that's a good question, because for nonlinear processes, somehow people believe that we should have a resonant excitation of modes or particular resonators at the fundamental frequency, but it turns out that some of the effect can be better controlled by designing resonances and the harmonic field. The same valid for emission. For example, if you pump structure and then see emission at different frequency, like in the case of luminescence, so resonances should be carefully designed, but there is no general answer yet. There are several examples. So it's a rapidly developing field, and people trying different approaches. But it turns out that if you design resonances at harmonics, it may sometimes much better in terms of efficiencies, but it's not very well understood yet. So it's a field when more people require it to actually work on this. So it's a lot of fresh directions possible here. Yeah. Thank you.
The other two speakers, anything to add? Well, if there's nothing, let's move on to, we have a question from the audience. So the Akhil Ramesh would like to thank all the speakers for the wonderful talks. And they have a question for Professor Varun. Can you please let us know the laser spot size used on the nano disk in your presentation?
Yeah, so we normally use microscope objective lenses to focus the light. If you're addressing an individual meta atom, then we want to be comparable. The spot size should be comparable to the diameter of the meta atom. So we typically make use of maybe 2 micron or 3 micron spot diameter on the sample. But if it's a meta surface with many, like an array of meta atoms, then it's better to, if you're looking at collective effects, then it's good to spread that energy across the array, right? So maybe a lower numerical aperture and a larger beam spot size would be preferred.
So I guess next up, we'll have a question for Professor Park, more suitable for the Journal of Device, of course. So what are the key challenges in making these single photon emitters more practical for real world applications? And what sort of applications have, I guess, the most demand for these materials and devices?
Yeah, just key challenge is not just generating single photons, but efficiently coupling the emitter to a cavity to achieve pulsar enhancement. And also, just more practically, the collecting single photons to an optical fiber is more important, and high brightness and collection efficiency and indistinguishability should be maintained in this case. So that is most challenging issues. And so, but my group is focused on some integration of single photon emitters to high quality optical cavities for practical applications.
So is there any specific practical applications, I guess, that is driving most of this demand? Is there what kind of specific applications is driving the demand of these devices, of these single photons emitters? I'm just asking that from kind of like the industry or commercial point of view.
Right. So just there are several quantum technologies, including just quantum sensors and quantum communication and quantum computers. But just quantum computer to demonstrate and just photon qubit is not easy, just always challenging. But quantum sensors and quantum communication, especially quantum communication, the single photon is very good candidate. Also, in combination with single photon and single spin, and just photon can serve as a flying qubit. So just we can transfer the information to the other people just with very high security, and that will be some future technology for industry, in my perspective.
Thank you. So the next questions, I think, is for Professor Raghunathan. And the question is, what role does material absorption play in the efficiency of the nonlinear optical process?
Yeah, so often when we do frequency up conversion through nonlinear process, there is like a good chance that the energy of the photon may fall above the band gap, and then the photon will be absorbed, right? So that so then one has to look at the thickness, the interaction length, and then how does it compare with the skin depth of this material, and then see if it is going to be absorbed significantly or not. But often absorption is a parasitic effect. It would be good to avoid, and that's why materials with wide band gap are generally preferred, and that's what we try to find: high refractive index, wide band gap materials, which are always good for doing nonlinear optics, especially when we are doing frequency up conversion. Yeah.
Okay. Next, I think we have a more technical question, which is, can cavities with higher rotational symmetry enable the generation of higher order optical vortices?
Yeah, that is my part, and it's possible. And just in technically, and rotational symmetry generally restrict some angular momentum to maximum value is half of the value. So by increasing the rotational symmetry, is totally possible. So designing cavity with higher rotational symmetry can generate higher order vortices. So just we on the study to make higher rotational symmetry cavities.
Very nice. So just to close out the Q&A session, the last question is open to any of the speakers who want to hop on. Is what kind of optical intensities are used for the incident excitation, and so are the metasurfaces prone to damages at these intensity levels? Do we have to consider the intensity?
So for nonlinear optics, we do use high optical intensities. It could be on the order of few hundred megawatt per centimeter square to maybe few hundred gigawatt per centimeter square. Right. So so that is required as a way to compensate for the reduced interaction length. But one good thing with working with dielectric materials like silicon or even 3-5 materials is that they have a fairly high optical damage threshold. So they're able to withstand the high optical intensities. But eventual goal beyond proof of concept demos is like when we improve the conversion efficiencies higher, we can go to lower excitation intensities as well, right? So that would be required if for any of these demos to find some useful application. So definitely the field as a whole is going towards improving conversion efficiencies and reducing the incident light intensity.
Thank you. We do have one more question from the audience for Professor Park. The question is, what about tuning the emission wavelength of single photon emitters with TMD material, and also the stability of the emission? So how long will it make the same quantum state, I guess, using this strategy?
Yeah, that's very important question and very good question. But yeah, this is hard to say. So TMD material is very great to make a well-localized quantum dots, artificial quantum dot, but there is some still problems. So that is challenging how to control the emission wavelengths, because the TMD defect can emit single photons, and also stability is not very good. So that is the key challenge to single photons from TMD materials with some high quality optical cavity. These are also very challenging. So still people think about that, or more recently, other types of two-dimensional materials, for example, perovskite or boron nitride, and other candidates are now under study. So yeah, that is still, we should think about that.
Oh, thank you again for all three speakers for their time. And I think I'll hand it back to Panuta for any closing remarks.
Sure. Thank you. Thank you. As over and over again, we have iterated that 2D materials are our favorite, but it remains challenging to do the research stably and solidly. But yeah, we are excited, and then we follow up, in the next occasion. So I would like to say that we have come to the end of our session today, and again would like to thank all of our speakers and coordinators to organize this webinar for CellPress, Professor Yuri Kivshar, Professor Varun Raghunathan, and Professor Hongyu Park. It has been an immense pleasure to listen to you and for your presentations and engaging discussions. I would like to thank the audience for tuning in today to learn more about Metaphotonics. If you have missed anything during this webinar or would like to listen to it again, a recording will be emailed to you shortly and posted on cell.com events. Please take a few moments after this webinar to complete a brief survey that will be emailed to you momentarily. Your comments help us improve our service and value your feedback. Thank you so much again, everyone, and we hope to see you at a future CellPress event.
Thank you. Thank you very much for organizing that.
Thank you so much.
Thank you.
Thank you.
Thank you.
Bye.